So the net gate charge, okay, net gate charge is being supported by the inversion charge and the depletion charge now, but the concentration of these electrons are much higher than the depletion charge. Okay, so most of the increase, okay, most of the increase is going to come from the inversion layer. That is because now your bands have been so much. So any additional charge, okay, we saw that earlier we saw that. So this is the, if this is Vg and this is psi s, okay, psi s, we saw that, okay, so the psi s may increase and finally it gets pinned, okay, at accumulation and inversion. So this is what happens here, your surface voltage gets pinned here, okay, that means there is not much change in the voltage and there is no, but because any small change in the voltage, surface voltage, okay, it can create a large number of electrons, okay, so it is practically, there is no modulation at the surface voltage. So what it results is, okay, this situation is also very simple now. So you have some charge at the gate, you have some sheet charge at the interface. So what it results is nothing but, okay, you will get back to your parallel plate capacitance like scenario. Okay, so that is, you have only Cox here. Okay, that is because your surface is now pinned. Okay, it's essentially it's similar to an accumulation condition. Okay. But your charge, so but here your charges is, one is positive here, here it is negative here. That's the difference. So that is what happens here. So from depletion, okay, because you no longer have the depletion charge, okay, so you no longer have the modulation of the depletion width, okay, so you have the depletion, okay, you have to keep in mind even at inversion there is a depletion layer, okay, but its width is not modulating, okay, if it is not modulating that means there is no capacitance, okay, but still the depletion layer exists, okay. So it goes back to a higher value, okay, so that is why at accumulation and at inversion, okay, it is more or less same as a Cox. So that is why this MOS capacitor, okay, it has got a nonlinear capacitance, okay, so it's not a fixed quantity, it's not a some multiple it's not varies linearly with voltage, okay, it's a highly nonlinear capacitance. So it is, and so you can say first it's a high value, then it decreases, then it increases back, okay, so it's not even a monotonic capacitance. So but now if you look at this capacitance, okay, so if I vary the frequency of the AC signal, okay, the AC signal, that is this is the AC voltage which we are going to measure the capacitance. So you can see something interesting, okay, depending upon the frequency of the AC signal, okay, you get two kind of capacitance at inversion, but you don't have that problem in the accumulation, okay. So depending upon whether you use a low frequency AC signal or a high frequency AC signal, you get two kinds of capacitances. That is because we saw that the inversion layer, especially in a MOSFET, okay, it comes from the Shockley-Rithold, the traps, right? The inversion layer comes from the generation from the traps, okay. So it takes some time, okay, it takes some time to build the inversion layer, okay. So typically if you, this is from the Shockley-Rithold theory, so the time required to build an inversion layer, it is roughly 2 times Na tau 0 by Ni. Okay, so the tau 0 somewhere it will be some couple of microseconds to milliseconds, it depends upon how many number of traps exist in the semiconductor. Okay, let's try to work it out. Okay, put some values. Na, suppose I like use 10 to the power of 16, so Ni is roughly equal to 10 to the power of 10, right? So the time, okay, the time, okay, the t is equal to, okay, so it is 10 to the power of 16. Okay, so if you multiply, okay, so if it is suppose I take some 1 microseconds, okay, so it is 10 to the power of minus 6, okay, divided by 10 to the power of 10, okay, so this takes, okay, it says it is like 1 second. So that means if you want to get, okay, if you want to get a low frequency, if you want to get this low frequency characteristics, okay, you need something like a 1 hertz signal, okay, so that's very small, okay, if you are engineers, okay, so if you are power engineers, okay, so this may be this is something like 60 hertz, okay, what is there in your supply voltage. But if you are a communication engineer, like you may be working with kilohertz or megahertz, or if you are a digital designer or something like, so you are comfortable with working at megahertz or gigahertz of frequency, okay, so this looks very small. If this is a device, okay, this looks very small. So that is what it says, that okay, if you want to get this low frequency characteristics, okay, so your AC signal has to be very low in frequency, okay. Sometimes it has to be, okay, if you want to get a proper AC, you need to be something like 0.1 hertz. But if you increase the frequency, okay, suppose you apply somewhere around a couple of 100 kilohertz, okay, or 1 megahertz or 1 megahertz. So the frequency characteristics what you get is going to get this high frequency characteristics. Okay, so you no longer have Cox here. Okay, so what happens is that, okay, it will reach a C minimum. Okay, somewhere around C minimum. Okay, so that is what is going to happen. Now let us see what is being happen. Okay, at high frequency what is going to happen. Okay, at high frequency characteristics, okay, you still have the inversion layer. Okay, it's not like there is no inversion layer. So the inversion layer still exists. Okay, but it is not able to follow the AC signal. Okay, that is the problem here. Okay, so suppose this is the inversion layer. If this is the inversion layer, so what is going to happen is, so if you increase the gate voltage, okay, so what happens is, okay, it has to increase by delta this much. Okay, but this is not happening. Okay, because it has to come from this phenomena, but this phenomena can supply electrons only at a very small rate. So if you apply very high frequency signal, so what is going to happen is that, so this inversion layer is not able to respond. So it reaches some kind of a plateau, it plateaus out. Okay, so what is this capacitance? Okay, this capacitance is, okay, so if you look at this, this 1 over C is equal to 1 over Cox plus 1 over C depletion. Okay, so this C depletion, okay, the C depletion, okay, we saw that the depletion width reaches some kind of a maximum at the inversion condition. Okay, so you can find the C minimum. Okay, so 1 over C minimum is equal to 1 over Cox plus whatever this is a maximum. Okay, so you compute the maximum depletion width. Okay, so you compute the maximum depletion width and then you can find the C minimum. Okay, so that is roughly the C minimum. So if you want to solve any problem, this is how you calculate this minimum capacitance. Okay, so there are two capacitance in series. One is the Cox and the depletion capacitance, the minimum value of the depletion capacitance in series. Okay, that, and since this is a minimum quantity, it pulls down the gate capacitance and the gate capacitance reaches a minimum. So any high frequency signal, okay, if your AC frequency is very high, this is the characteristics you are going to get. It comes something like this and like this one. Is that clear? So then this poses a dilemma, right? So that means you are not suppose you are going to, so essentially what we are going to do is you are training from accumulation, depletion and inversion. So that's a same condition which happens in a transistor. Okay, so transistor, when the transistor is on, we will see it is full of inversion layer. Okay, so the inversion layer is, the surface is inverted and it's full of electrons. So when it is off, okay, it may go back to somewhere here, it's a depletion. So it has to constantly switch on and back. Okay, so it has to go back like this one. Okay, so that means when you apply very large frequencies, okay, you should be able to turn off and on the channel. So if you look at any microprocessor, okay, any microprocessor in a desktop or in a cell phone or something, the frequencies are very large, especially if you are using a powered micro in a desktop, okay, it may be somewhere around 5 gigahertz or 4 gigahertz. Okay, now where does these electrons come from? Okay, so you need to constantly turn off and on the channel, but at this frequency. But if your depletion, if your inversion layer is not able to respond, okay, now it poses a dilemma. Okay, so where does these electrons come from? Okay, so now let us hold on a minute. Okay, so you can think about this question. Okay, where does these electrons come from in the case of a transistor? So what it says is that, okay, this in the MOS capacitance, okay, so we saw that the MOS capacitance, the capacitance is a function of voltage. Okay, that is depending upon where you apply at accumulation voltage, whether your surface is accumulator, whether it is depleted or inverted, you get different kinds of capacitance. Then other thing is that, okay, your capacitance is going to be a function of frequency. Okay, so this is, okay, so you're making a complicated passive element. So that is because at low frequency, if the frequency is very small, okay, you get somewhere around Cox here. Okay, so this in this case, okay, it's around 10 hertz. But you can see as you increase the frequency, okay, even from 10 hertz to 100 hertz, you can see Cox is going to go down. The capacitance, then from 100 to 1000 hertz, and if it's around like 100 kilohertz or 10 kilohertz or 1 megahertz, okay, so you then it doesn't change. So that means the inversion layer is not able to respond to the AC signal. Okay, you have to keep in mind the inversion layer doesn't vanish. Okay, it is still there, but it cannot supply the delta Q charge. Okay, it cannot go plus delta Q or minus delta Q. It's not able to supply that plus or minus delta Q charge. So, so your capacitance, okay, so it's a function of voltage and also it's a function of frequency. So, typically when you talk about MOS capacitor, there are two kinds of capacitor. One is a low frequency CV, other is a high frequency CV. So, in the high frequency CV, so you typically measure at 100 kilohertz or 1 megahertz. Okay, so because you don't want any uncertainties here. Okay, so yeah, you don't want 100 hertz or 1000 hertz. Okay, you typically you make sure that the frequency is very large. Okay, it's around 100 kilohertz and 1 megahertz. So, now let us come back to the earlier question I posed. Okay, so what's the difference? Okay, what's the difference in a MOS transistor and an MOS capacitor? So where does these electrons come from, or in the channel? How does the channel is formed when you turn on or turn off the channel? So that is because in the MOS capacitor, on the MOS transistor, you have something else along in contrast to the MOS capacitor. So you have something known as the source and the drain. Okay, so the source and the drain. So its function, okay, its function we will see in detail later. Okay, its function is to supply the charges for the inversion layer. That's it. So we will see later the exact mechanism. How does it supply? So what happens is that, okay, when you vary the surface condition to inversion, what happens is that the electrons flow from source and drain to the channel. That's all. So the source and drain populates this channel. Okay, so you don't need to wait for the thermal generation or for the generation from the traps. Okay, the electrons, okay, they just flow in from the source and the drain. So because the source and drain, they are very heavily doped. Okay, so they are electron rich areas, so they can easily supply those electrons for the channel. That's how the channel is created in the case of a MOS transistor. Okay, so that is why, okay, so that is why you are able to operate a MOS transistor in like 5 gigahertz, but you are forced to operate. Okay, if you want to see an inversion layer, okay, proper inversion layer capacitance, you need low frequency, that is like 0.1 hertz. So this the source and the drain. Okay, so because these electrons are being provided from the source and drain, that is why you are able to operate the MOS transistor at very high frequencies. So if you try to measure a capacitance, okay, if you try to measure a capacitance in a transistor, okay, if you can do similar, if you try to measure a capacitance in a transistor, okay, you always get a low frequency type of characteristics. Okay, so essentially you can tie this source and drain and you can measure the capacitance together. Okay, so for example, I can measure something like this one. Okay, so this is the gate. So what I do is that, okay, I tie the source and the drain together. Okay, then I measure the capacitance between these two. Okay, so that means there is a channel always. If the channel is always present, if I measure the capacitance, I will get I can get the full capacitance here. So now, there are some conventions in drawing the capacitances. Okay, so what you typically do is that, okay, you plot something known as a normalized capacitance. Okay, so you measure the capacitance and you divide by Cox. Okay, so you divide by Cox, then what you get is, okay, so in the accumulation it is 1. It is 1, and depending upon whether it's a low frequency or high frequency, okay, the low frequency also it goes back to 1 here, but the high frequency is somewhere at a lower value. Okay, so this is what is the substrate? This is a p-type substrate, okay, because the inversion happens for positive gate voltages, and similarly this is an n-type substrate. Okay, so here the inversion happens at negative voltages. So this capacitance, so this property, okay, so this property of this capacitance, for example, it goes from here to here like this one. Okay, so this property of capacitance, so you can see you have what you have at hand is a variable capacitor. So depending upon the voltage I apply, you get different capacitance. Okay, so you get the capacitance is maximum here, the capacitance is minimum here, right? So if you want to operate the capacitor if you want to use it as a variable capacitor, so you operate at a high frequency, then you always have a monotonic characteristics. Okay, so why you don't apply here is because one is you are limited by your circuit. Okay, your circuit you may be operating at a very large frequency, that is why you don't want low frequency capacitance. Other thing is that, okay, so this capacitance, it has two values, okay, depending upon it, this capacitance, at two different values you get this capacitance, so you don't want that. So you normally always operate this, whatever the MOS capacitor in high frequency condition, so you get a nice monotonic characteristics, okay, there is only one C maximum and there is only one C minimum here, right. So this, you utilize this property, so wherever you want to use a variable capacitor or something as a varactor. Okay, so if you want use a varactor, okay, so you use this MOS capacitor. Okay, so depending upon the bias you apply, you get different capacitance. Okay, for example, if you want to build a tuning circuit, if you want, how do you? So you have a fixed inductance and you have a variable capacitance. So you can tune the center frequency of a tuning circuit. So what you can use is that, suppose if you want a solid state capacitance. Okay, so not. So if you try to open a very old radios, okay, so what you have is like you will see a variable plate capacitor, okay, because it's a very bulky capacitor, okay, so you can see it goes in like this one and comes out, okay. So but here what you can have a nice compact solid state capacitance, it's a variable capacitance and you can use it along in a tuning circuit. So typically if you are a circuit designer, okay, what you are interested in is something known as a this is a metric, okay, this is a tunability. Okay, how much room I have, okay, so that is, this is a C maximum, this is over the C minimum, okay, this parameter is known as a tunability, okay, so this is not very large, okay, so you can see if you try to do the math, okay, it may be somewhere less than 10, okay, so you don't get very large tunability, okay, so this is typically less than 10, but you can see if it, even if it is less than 10 or something, okay, you can tune the frequencies in a sufficient bandwidth. So far we have been discussing, okay, so in the discussion we started, so far we have been discussing about ideal MOS capacitors, okay, that is because your oxide, okay, your oxide is a pure pristine oxide, but what happens is that in a real case there could be always some kind of a charges associated with the oxide, okay, there are various kinds of charges for so now the question is, where does this charge come from? Okay, where does this charge come from? Because oxide is an amorphous material. Okay, it's an amorphous material. Okay, there could be traps. Okay, there could be traps existing inside the oxide. The traps means so these traps these are the traps similar to what we saw in the Shockley-Reed hole in the bulk semiconductor. Okay, so there are similar traps inside the oxide. They can trap charges. Okay, they can trap charges, and if there are any charges present, it may modulate your threshold voltage or it may modulate your CV characteristics. So in any real MOS device, okay, there are always some charges. Okay, there are always some charges within oxide or at the dielectric interface. Okay, so if this is a silicon dioxide, okay, so this is silicon dioxide, there are various kind of charges. Okay, so you can classify, you can categorize these charges roughly into 4 categories. Okay, we will see one of them. Okay, so one is, okay, you can have charges right at the interface. Okay, you can have charges right at the interface between silicon and silicon dioxide, and other case, okay, you can have some charges slightly away from the interface. It's slightly away from the interface. You can have charges which are distributed inside the oxide. Okay, it can be, you can have positive charges or negative charges distributed inside the oxide. So let's take one case. Okay, this is QF. Okay, this QF, they are fixed charges. These are mostly positive. Okay, these are positive charges. So these are mostly come from. Okay, these are mostly come from during the oxidation process. Okay, so where does these charges come from? Okay, so first of all, how do you create this layer? How do you create this layer? So this layer is created. You oxidize the silicon. Okay, so you take silicon here. You oxidize the silicon. Okay, so you essentially use a dry oxygen, you pass dry oxygen and you at very high temperature, okay, something like 900 to 1100 C. So what happens is that the silicon reacts with oxygen, okay, and it consumes a layer, okay, it creates a layer of silicon dioxide. So it creates some silicon, it consumes some silicon, so it is converted to silicon dioxide here. So some of these charges, it can be created during the oxidation process. So then the question is, okay, so apart from changing the VT, apart from changing the CV characteristics, okay, so what are the problems with these charges or the traps? Okay, So the problem with this one is if there are present, if the charges are present here, it will affect something known as the time zero performance. Okay, time zero performance is that, so you have some capacitance or some VT or something of the device. Okay, you calculated this one. Okay, using hand. Okay, if you know the doping or something, you can calculate this one. But if and you calculate it at some VG. Okay, so you predict at this VG I am going to get this some capacitance. But if there are some charges present, okay, if there are some charges present, what happens that you may get a different capacitance. Okay, so that means you are not, your prediction is wrong or your calculation is wrong. So that is known as a time zero performance. Okay, for example, if you are using this capacitor as a varactor, so you are expecting some capacitance at some gate voltage. Okay, but if there are some charges present inside the oxide, your capacitance could be different. Okay, so the capacitance is different, your center frequency of your tuning circuit could be different. And other important problem is that, it may affect the long term reliability of the device. Okay, so the long term reliability is that, okay, so you may have very good device at t is equal to 0, at t equal to 0, very good device. Okay, the device was good, but as t progresses, what happens is that the device undergoes something known as stress. Okay, some kind of an electrical stress. Okay, so just like students feel stress for exam or something. Okay, because you are continuously operating this device. Okay, what happens is that the device undergoes this stress. So you can have gradual buildup of these charges. Okay, especially like the trap charges. Okay, you can have gradual buildup of charges inside this oxide. Okay, if there is gradual buildup of charges, okay, that means your capacitance is going to be a function of time. Okay, so all your VT, the capacitance, everything becomes a function of time. Okay, I am not saying that changes in a fraction of milliseconds or something like that, but over time, okay, over the lifetime of the device. Okay, suppose you measure it today, maybe 6 months later, 1 year later, 10 years later. Okay, that is why that typically all these electronic devices they have 10-year lifetime. Okay, that is because over continuous use operation of these devices, what happens is that these charges get accumulated inside the inside the dielectric. Okay, what happens is that it will shift the characteristics. Okay, it may shift the characteristic of a transistor or a capacitor, and if it shifts so much, okay, typically if you are a circuit designer, they may assume some margin. Okay, so my device may shift. Okay, the characteristics of a device may vary within a band. Okay, that's something known as a design window or something. Okay, but if the device shifts so much and if the device is beyond the design window, what happens is that, okay, your circuit may malfunction. Okay, so that is why it is very important for the long term reliability of the device. Now let us take one particular case. Okay, Okay, so there are various. So you can see there is one quantity here. This is something known as the mobile charges. Okay, it comes from the presence of alkali ions. Okay, this is the sodium or potassium. If there are present, it will contribute to mobile charges. And if there are any oxide trap charges, okay, that will contribute to QOT. If there are any interface charges, because if you see here the interface, okay, this is silicon here, this is a pure crystalline material, and you are changing your material from a crystalline to amorphous here. So there is a sharp material discontinuity. So what typically happens is that there are a lot of traps at the interface. Okay, so these traps can attract charges, it can trap charges, it can scatter charges. So that is why this is the interface states. So there are different 4 categories of charges. Okay, let's take one of them, that is known as a QF, that is a fixed charges. So this is a fixed charges. Okay, so typically these are positive charges. Okay, these are mostly positive charges. They lie at very close to the interface, okay, roughly around less than 2 nanometers from the interface. They are mostly caused by, earlier I explained the oxidation process. Okay, typically you you expose the silicon to a dry oxygen or a dry oxynitride ambient. So you convert to silicon dioxide. So if there is any incomplete oxidation, okay, so if there are any incomplete oxidation of the silicon atoms, okay, what it creates is this fixed oxide. So typically what you do is that after the oxidation process, what is typically done is that you do some kind of an anneal. Okay, so that is you keep the wafer in a argon ambient. Okay, inert ambient. Argon is a noble gas, so it doesn't do anything, it doesn't react with silicon. But what it does is that, okay, it can reduce the number of fixed charges. So this is very important. So you do a post oxidation anneal in an argon ambient. So now let us see what is going to happen. So what is going to happen if there are positive charges. Okay, if there are many positive charges, so now let us assume if it's a p-type semiconductor here. If it's a p-type semiconductor, and if you are trying to invert the channel, okay, if you are trying to invert this MOS capacitor, if there are positive charges here already present, okay, if you have positive charges already present, that means, okay, this positive charges, okay, it can attract negative charges here, right. So if you are trying to invert these charges, a positive charges, what happen? It can happen. It can create the inversion layer earlier. Okay, earlier means in terms of gate voltage, at lower gate voltage compared to a case where the QF is equal to 0. So if the QF is positive, that means your VT is going to go down, is going to decrease. Okay, and this will get reflected in your CV characteristics. So now let us take this case. So this was your high frequency CV characteristic. For all these cases, we use the high frequency CV characteristics because they are clean. Okay, it goes from a maximum, it goes to a minimum here. So if you have positive charges, okay, if you have positive charges, what is going to happen is that, okay, it is going to shift these characteristics towards the left. So you can see, suppose earlier your VT was somewhere here. Okay, now your V, if there are, this is your VT has even reduced to negative voltage because if there is if this QF is very large. So how much is the shift? Okay, how much is the shift here? Okay, so how much is the shift delta VT? For example, we can calculate this delta VT is nothing but Q times this electronic charge multiplied by Q off by C ox. This is roughly the amount by which it is going to shift. So you can see, so this is the same thing. Okay, so suppose you are a circuit designer. Okay, so you had biased this voltage here. Okay, suppose now you can see if you if there is a shift charges, so in the ideal case you are expecting somewhere here, but now you are going to get this capacitance. Okay, that is why this is important. Okay, the time zero performance of the device. Okay, it can so happen that this build-up of charges could be, okay, it may not be fixed charges, some other charges, it has shifted the characteristics. So you can see the characteristics of the performance of the device. Okay, it is going to vary. Okay, it's going to drift. Okay, it's some kind of a drift in the characteristics over time. So that is why these charges are very important and we have to keep in control. So you don't operate the device so you don't choose any bias condition in such a way that, okay, the device undergoes a large electrical stress. Okay, that is why every transistor, okay, it has an operating voltage. Okay, typically it is specified that you should not go beyond 10%. Okay, what happens is that if you apply a higher voltage, what happens is that, oh, you are going to stress the device. You are going to stress the device and you are going to have this kind of a charge accumulation. Okay, so that is going to affect your lifetime of your device. Let's come back here. So this is a case of positive charges. So had the charges been negative, okay, what is going to happen is that, okay, so if the charges are negative, suppose this is the interface and there are a lot of negative charges here inside the oxide and this silicon. So that means you are you are making it harder to create the inversion layer here, because these electrons will try to repel whatever the electrons in the inversion layer. So that means you need to apply higher and higher voltage to invert the channel. So your VT increases now. In this case, your VT increases. So your VT increases. That means you are so now the same thing here. Suppose you are a circuit designer. Okay, suppose this was the bias voltage you are applied. So you are expecting here, but okay, this is the capacitance you are going to get. So you can see either way, whether it's a positive charge or negative charge, okay, it's going to shift the characteristics. And for example, if your substrate is N-type, okay, this is an N-type substrate. Okay, so you can see this accumulation is here, this inversion is here, this accumulation. So if the charges are positive here, okay, if the charges are positive, that means you are inverting, your inversion layer is composed of holes now. So if it is positive, okay, then it will repel. Okay, so it's a simple picture is it will try to repel away the holes. Okay, so that means you need to apply large more and more negative voltages to create the holes. Okay, so that means your VT, the mode VT, okay, the modulus of the VT, it again increases here. Similar, but if it is negative, you can see it is like attracting holes. Okay, so the inversion layer comes early, okay, or at lower gate voltages. Okay, so it will shift in this direction. So what it says is that, okay, so if you see, if you measure the gate capacitance, okay, if you measure the gate capacitance, and if you see it's quite different from what you have been expecting. Okay, so that shows that, okay, if you are thorough with your calculation, that means, okay, there is some some kind of a non-ideality which is existing in the oxide. Okay, so that is why this MOS capacitor, it's like a good process monitor. Okay, so it can catch any issue. Okay, any gate oxide related issues. Okay, using electrical ways. So what you do, you build a capacitor, you measure the CV characteristics, then you compare it against your ideal capacitance. So from there, the shift in the characteristics, you can infer like whether there are some kind of an oxide charges present, and then what kind of oxide charges present. In this case, I have given only a simple case. There is a parallel shift in the CV characteristics. Okay, but in real case, okay, it may not be a truly a parallel shift. Your CV characteristics could be skewed. Okay, so based on all these things, you can this is some kind of a detective work, right? So something has happened in your process. So you can, based on the CV characteristics, you can decide, okay, what might have gone wrong. Okay, so then you can tell this to the process engineer. Okay, maybe in which process in module it might have gone wrong. Okay, so maybe I will stop here for this session, and maybe I will take up some questions before moving on to transistor. So we will stop for 5 minutes to take up any questions on the any from previous lecture or the lecture, the MOS capacitor. Okay, there is a question, how temperature affects accumulation, inversion, flat band capacitance. Okay, that's a good question. So the accumulation capacitance, okay, for example, temperature, when you vary the temperature, okay, so when you vary the temperature, and the accumulation capacitance doesn't change as much, okay, but it may affect your inversion capacitance or your depletion capacitance. So inversion, for example, okay, so if you increase the temperature, what happens? You are increasing the thermal generation rate. Okay, if your thermal generation rate, if it increases, that means you are making it easier and easier for the electrons to generate. So this low frequency. Suppose earlier, if you want to wait till 0.1 hertz to get the low frequency characteristics. Okay, if you increase the temperature, that means you can get at a slightly higher frequencies. So that means the inversion channel is able to respond, okay, at slightly higher frequencies. That is because at higher temperature your generation rates may increase. That's the same thing with the optical excitation also. If you shine light, okay, okay, so and if you try to measure the capacitance, okay, if you shine light, okay, so your photons are generating electron holes, okay, so in that case also you can get, so that is very important. If you are trying to measure any MOS capacitor or something, you make sure that the temperature, the temperature of the chuck or something, it's at room temperature and there is no light, okay, there is no ambient light or there is nothing is falling on the MOS capacitor, otherwise it's going to shift your capacitances, CV characteristics. There is another question, do interface trapped charges in MOS capacitor? Sorry. So this trap charges, okay, so the trap charges also may shift, okay, because that question is gone. The current question is, okay, what is the effect of trap charges on the series capacitor? So if there are trap charges, okay, if there are trap charges, okay, so that means if this is like this one, so if this is your oxide, for example, this is oxide, or if there are trap charges here, positive or negative, something like this one. Okay, so you have a distribution of charges somewhere here. So what you can do is that if this will also shift, okay, but the amount of shift, okay, if the charges are very close to the interface, okay, so very close to the interface, they are more effective compared to the charges in the bulk of this. So for example, if there are any charges at the metal and the say oxide in the interface, they are not very effective, okay, because they are far from the channel. So those charges which are closer to the interface, okay, they are more effective. So if you have a distribution of charges, suppose you have a rho versus x, okay, so if you have a rho x, so what you can do is that, okay, so you can find an effective sheet charge which is at the interface, okay, so how do you find it? Okay, so this is like rho x, okay, you integrate by dx, then how do you do this one? Okay, so this you find the total volume and you find the integrated sheet charge at how far it is there. Okay, so you can find the integrated some kind of an effective charge. Okay, we can have an effective charge and you can lump all the distributed charges as a single lump sheet charge. Okay, and okay, so that sheet charge, depending upon the distribution, it could be somewhere here or it could be here. So if it is close to the metal, okay, if it is close to the metal, then they are not very effective. So this is, so it has to be close to the semiconductor for it to be very effective. Another question is, okay, in linear mode operation, which parasitic capacitance exist? Linear mode means, are you talking about the linear mode of transistor? Because there is no linear mode in the MOS capacitor, or are you talking about in the depletion region where the, could you clarify that question?